So my name is ChristopherLiljenstolpe. I just recently came into the formal OpenFlow community. I was recently, until a couple months ago, the chief architect for Telstra down in Australia, but I've stopped standing on my head now. I'm back on the upright portion of the world as of a month and a half ago. So I'm going to talk. I've been in and out on more on the carrier side. So I'm going to talk about some of the other places other than cloud where OpenFlow and software-defined networks might find their use. The topic, when protocols are abused, a number of times in my career, my business card has actually had the title heretic on it. So I view my role as one of saying why or why not. So we're going to talk a little bit about, what you can do if you abuse, what kind of interesting things you can do if you abuse protocols. And by abuse, I don't necessarily mean violate, but maybe use them in ways that were not originally use cases that were thought of when the protocol was designed. One point of order, we've had a couple of requests, and I think it's a good idea. When you ask a question, if you can just state your name and your affiliation, it might also help for people get to know other folks in the OpenFlow community a little bit better. Figure out what your interests are, and maybe you can build up, have an offsite conversation. That's easier if you actually know who was asking the question. So I'd ask, when you ask questions, if you could put your name, if you could say your name is and who you're affiliated with, that might be useful. So, as I said, and as in the intro, long service provider history, in and out, started at Internet MCI / Cable and Wireless back in the late 90s. Vendors in that space, operators in that space, and what I'm going to talk about is the squeeze that the service providers, the big backbone providers, and the RBOCs and the PTTs around the globe are facing. Most of them have built their business model around undifferentiated, what I'll call undifferentiated heavy lifting. Carriers are very good at building large pieces of infrastructure and replicating that and selling basically the same set of services off of that to a lot of different people. It may be packaged differently, it may look differently, but it's basically the same process, it's the same product, reskinned different ways. To date, for a lot of carriers, that's been pushing bits around a wire. There's not a lot of high value in that, no matter what service providers will tell you. It's not an easy job necessarily at scale, but there's not a lot of value. Most companies don't want to buy, with some exceptions, internet or network services. That's not what their business is involved in. Their business is involved in what they're buying that network connection for is to do video conferencing, to tie their offices together, to communicate with their customers, to have a web presence, to do scale out compute clusters in order to calculate the risk values on bonds. There's many things that people need a network for. As a general rule, they don't need a network for a network's sake. That's an awkward position to be in if you're selling a network. Because if I don't need a network for network's sake, I just need it to do something else. It turns it into a commoditization game pretty quickly. So the only way to make money in a commodity market is to either A, move up the value stack, or B, strip as much of the cost as you can out of that infrastructure, or out of the non-customer facing parts of that infrastructure, to actually spend the money to develop the services that people actually want to buy, and to reduce your cost base on the things that are the necessary components of your business, in this case, say a backbone, that frankly most customers are never going to see nor care about, no matter what your marketing folks believe they can spin. So, I would much prefer to spend my money where my customers see value. So I can extract a higher margin, I can extract more value from that, I can be more closely integrated with the customer, I can give them something that they want rather than a necessary cost that they try and avoid. Bit transport is not that today. Pains me to say it, because I'm a bit transport guy, but pushing bits around the wire just doesn't have a lot of value today. Same thing, most service providers have existed in a world where you make a couple of bets a year and you do things very large. Everyone talks about service providers being slow to react, slow to change. Service provider business model is you spend a lot of time thinking about something, because when you do infrastructure, you do it large, huge CapEx outlays, huge OpEx outlays that take years. If you get it wrong, you'd be years down the track before you realize you got it wrong. So you spend a lot of time up front navel gazing and thinking about if you got it right, and then you pull the trigger and you spend $1 billion. So that's great for doing things at scale if I'm doing the undifferentiated heavy lifting, if I'm putting in a big infrastructure to move bits faster, quicker, cheaper, whatever. It's very poor when my customers come up with a new idea for a service they want to buy every 3 months, or every 2 days, or every 1 day. So service velocity, feature velocity and volume must be on the same order of magnitude as the over-the-top providers. So the nemesis for the service provider today is the over-the-top guys, and there are some over-the-top guys in the room here. And the reason being, the over-the-top guys basically can provide, they're building huge infrastructure, but they're building it at a different layer in the cloud, in the infrastructure, and they're able to do in software many things fairly fast. It's a software rather than a hardware rollout. It's a software feature velocity. Writing code takes somewhat less amount of capital and time than, say, not saying it takes short period of time or doesn't require some capital, to say rolling out a new backbone. So they can try more ideas, they can try them faster, they can iterate much faster, they can put something out for a week and see how it's taken up by the market, and if the market doesn't like it, change it. It's a little hard for me to rip wires out of the ground because somebody didn't like that approach. So that service provider velocity has been much slower. In this industry, in this market today, people don't want slow innovation. They don't want their service provider coming to them and saying, in 3 years I can give you this. They want this in 2 weeks, and if you can't give it to them, someone over the top will. And again, that pushes you in to the undifferentiated heavy lifting and the non-profitable bit. I become the necessary evil cost to allow you to get to your over-the-top provider who actually is providing the service you want. So unless I can get, as a service provider, into this feature velocity and volume, I'm not going to be the same volume and the same feature velocity as an over-the-top guy, but I need to be somewhat competitive. If I'm going to roll services out, I need to roll them out in periods of months, not years. In order to do that, I need to spend more money in the services area, which means spending less money somewhere else. So, what I need to do is, like I said, change where my capital is allocated, change where my OpEx is allocated. Some of the things that drive economics for a carrier, and this is what I call core economics. You can't sell it. I can't sell a customer core. I can sell very few customers my core network. But I can't sell without it. The whole underpinning for a network service provider is their network. So I need it to sell, but no one's going to buy it directly. It also becomes interesting in this case is that when I go make a case to make a business case for extending my core, I can very easily, usually as a service provider, make a case for extending the edge of my network or the services of my network. I can say, I'm out of edge routers, you can't turn up any more customers. And the bean counters can look and say, well, you're out, you've got 10,000 ports, you have 10,000 customers, we want to turn on the next 5,000 customers, you don't have ports for them. So therefore, it's fairly easy to put the case in and say, I need 5,000 more edge ports, or I need 5,000 more ports on a voice PBX, or whatever. Core is a little more fungible. No customers are directly connected to it. The bean counters, it's hard to make a case. It's much harder in reality to make a case for extending core. They'll say run it hotter, run it tighter, oversubscribe it more. So it's hard to make the business case to make investment in the core. Over time, I see this problem will also morph into the core of the big data centers. Most large data centers, until somewhat recently, say within the last 5 years, have been very much almost statistically planned. North, south, tree-based architecture. Requests for information come in, they get served by a given server that holds that information and the data returns. So it's very much a north-south flow or very architecturally defined lines. As we go to mashup applications, we go to more cloud-driven applications where lots of service platforms are talking to one another, we end up with a lot of the same behaviors you see in a, say, internet backbone cloud. Any-to-any communication. A lot more traffic east-west than north-south. You have basically a large mesh of communications rather than a north-south flow of communications. In order to do that, you have to build a different style of core. It's one of the reasons people talk about open flow in the data center model of how do I build fat tree or closs networks or whatever in the data center to handle this kind of traffic flow. It's the same thing we were doing in service provider backbone networks 10 years ago. So, I keep on hitting the wrong button. Because of the any-to-any unpredictable flows, they're not really forecastable. They're not the same as the north-south flows. They go anywhere. They're dependent on what workloads are running at that given moment. So I have a lot more unpredictability in the network, so I need to start building my core network in the data center to look a little bit more like a backbone network. And it's unforecastable, unplannable as to where a lot of that traffic goes unless you control everything in that data center. The law of big numbers helps. Once you've got a lot of traffic doing any-to-any, I pretty much know what the capacity I need in the backbone, in the network is, or the backbone is. I just don't know where I need it at any given point in time. This is the internet backbone problem. So I know the size and scale of the capacity, I just don't know what the connectivity graph should look like. So what I'm saying is, what I'm talking about here is some applications for core. I'm somewhat convinced that over time we'll be having the same kind of conversation in the big cloud data center. This is not a happy graph, so this is the economics problem I have as a backbone provider. In 1998, I could charge $1,200 a megabit per second per month for transit. This is an exponential curve with a fit of 0.98. I get down here, and in 2011, according to the last numbers I pulled, people are saying $1.25 a megabit per second. I know the number is lower than that. I know it's sub $1 in places. And if you keep projecting out, basically says 63 cents a megabit per second for internet transit in 3 years' time. I'll guarantee you the price of building the backbone using classical mechanisms is not keeping up with this curve. So this is a very unhappy graph for a service provider. So, how do we sustain the business? One is to reduce the CapEx cost and the heavy lifting, and I'll say it here because I want to be pejorative, slightly less intelligent core. There's another term that's used in the internet community, dumb core, smart edge, but I won't call it dumb, I'll just say slightly less intelligent core. You also want to simplify the operation of that core network. Remember, the core is something I can't sell. It doesn't have value directly. So if I can reduce the cost and still have it function as a core and deliver the capabilities I need, but I reduce the operational expenditure and the CapEx by making it easier to manage. What I can actually do is take that CapEx and OpEx that I was spending in the core and redirect it to service creation at the edge where there's actually value and I can try and remain relevant to my customers. So this is how it's done today. I think I excised almost, okay, there's one label up there. If you know enough carriers, you'll recognize whose network this is. And if you look at a service provider network today, you have a whole bunch of services on the edge connected by a whole bunch of aggregation routers. Those aggregation routers connect to core routers, labeled as Ps here. And they traverse this core. This is the core we're talking about. And they get to another core router at some other exchange and push data out to all the service edges on the other side. So customer traffic coming in here is going to another customer out here, takes the path, say like this. One of the things to maybe make this easier, this router has to do quite a bit of work. It has to look up in the global routing table where this packet's eventually going, has to consult its topology, figure out what endpoint in the network it needs to go to send the traffic flow. So there's quite a bit of stuff it needs to do at packet time. There's a value in this core router. The problem is the way we all built these networks, this is the same core router. So this core router here might also have traffic that is connected to it that needs to go onto the network. But let's say in the United States, this is Omaha, and this is Los Angeles, and this is New York. In a classical core architecture, Omaha has to be sized not just for the traffic that's going in and out of Omaha, but also in this case, the traffic that's going from Los Angeles to New York. So all of a sudden I'm spending a lot of money on a fairly capable router that for most of its traffic is just making the same decision that was actually already made in Los Angeles. Don't need to remake that decision again. We know the traffic's going to New York, but because I'm using the same platform for what's called transit traffic, I'm basically paying again and again and again across the network to make the same forwarding decision. In a slightly larger image, and I started looking through my file system on my laptop and realized almost all the network graphs I had were covered under NDAs, so I grabbed the Internet 2 graph. This isn't under NDA. You've all paid for it if you're American taxpayers, so I figured this is a reasonable one to discuss. If you take a look at the way the network is basically designed, traffic, like I said, out of Seattle or Los Angeles is going through Salt Lake City, Kansas, Chicago, all along the line, say, to Washington, D.C. If Kansas City isn't generating as much traffic as, say, Los Angeles or Seattle going to New York, I still have to dimension Kansas City for the amount of traffic that's going through Kansas City. So I basically am spending expensive router ports to handle traffic where the forwarding decision has actually already been made in the network. Is there potentially a better way to do this? And I'll come back to that graph in a minute. What if instead you took those edge routers, so these are these PE and aggregation routers here, and the core routers here, and I interconnected them with a big switching fabric. And I want to pick a switching fabric that is going to have the best price curve over time. It's very hard to bet against IP and Ethernet. And one of the issues with costs today in the service provider network, not a lot of people need to buy very large MPLS switches. So the number of MPLS ports that get shipped is relatively small in comparison to, say, 10 gig Ethernet switches. All the cloud providers out there today need to buy lots and lots of 10 gig ports. The economics are going to drive the cost of 10 gig switching down at a more rapid rate than the cost of MPLS switching. Chip economics. So if I stitch all of the routers together with a large Ethernet fabric in the exchange. So now instead of using ports to tie the core routers to the edge routers one-to-one, I'm actually going through the Ethernet switch and I'm only buying enough ports on these routers to handle the aggregate traffic load from the edge routers to the core routers. I've saved some costs. So instead of stitching the edge router to the core routers, I'm actually only connecting the core router with enough bandwidth that it's going to need to talk to the edge routers it serves. So I've already reduced some cost. A number of service providers have already done that. But now what if I take this Ethernet switching fabric and I use it to interconnect the core routers at the different sites? Now this is not running an Ethernet network. This is not running spanning tree. Maybe it's using OpenFlow to signal paths between core routers in the network. I'll guarantee you the cost of a 10 gigabit port on an Ethernet switch is just a little bit cheaper than the cost of a 10 gigabit port on a router that has full internet tables. Maybe just a little bit. Or maybe a little more than just a little bit. I still need those ports, but do I need a core router here, say in Omaha, to make a decision that this core router in Los Angeles has already made? So maybe this core router in Los Angeles puts the traffic into the Ethernet switch labeled with a MAC address or a VLAN or something else that says, this is going to New York. And a controller has provisioned, a network of controllers have provisioned this entire fabric to say, traffic coming in from this core router in Los Angeles going to New York takes this path through the network. And it has a backup path as well. So all of a sudden, I'm reducing the cost for this fairly simple transit function, and I'm repurposing it so I can put more interesting features in the core routers and edge routers, which actually are what provide value to my customers. Or maybe the server farm that's sitting off here that's running, server-based applications for my customers. I could do this today, but you're going to do it sort of in a custom one-off way. If I had a bunch of Ethernet switches with, say, OpenFlow controllers, I could use a heterogeneous collection of switches. I have a global topology view, and that's where it becomes interesting. You don't want to run spanning tree to keep this loop free. If I run spanning tree, most of the bandwidth is going to get blocked, because you actually want a fairly rich connection mesh between these switches. If I run, say, OpenFlow, the controllers keep the topology loop free. I don't have to run spanning tree in the network. My loop free environment is maintained by the controllers. That way I get to use all of the bandwidth for all of the interconnections. I basically built almost like a cloth network across the infrastructure. So, how is this better? Traffic engineering. Going back to the graph. Most service providers have a pretty good idea of how much traffic they flow from any given router pair in the network over a given period of time. That's part of your bread and butter, because you have to use it for planning how many links you need and how much. You can't turn up a new fiber in a period of weeks. I need to give the planning guys a little more time than that, usually months or years. So what I need to do already for my business is keep track of how much traffic flows from this core router to this core router, and from this core router to this core router independently. So I already have that graph. Law of big numbers helps me. Traffic patterns might change, but it's always going to be basically the same when you aggregate enough of the traffic together. So I can basically project into the future how much traffic I need between any 2 points in the network. Once I do that, I can put that into a tool, say for example, and solve the graph. A tool that knows all of these links and knows which links will fail together and which links will not fail together. So I can build a resilient graph that basically takes all of that traffic and lays it into the network by telling the controllers, and the controllers provision that set of paths into the network. I could also make this reactive. The controllers could theoretically, or not theoretically, could also, if I was so inclined, monitor the network and say, this link is getting hotter than I thought it should be, or this link has failed. So I'm now going to recalculate the network graph, and I'm going to move the traffic from Los Angeles going to Atlanta. I'm not going to send it on this link anymore because it's hot. I'm going to send it through Kansas City to Raleigh first, instead of Dallas through to Atlanta. So I can pick up and move flows at the controller. The routers are never going to actually realize the flow has gotten moved. The router will still see a direct connection from Los Angeles to Atlanta. If that link's failed, I can move all of the traffic. So instead of carriers talking about 40% utilization, I have to have all, backup bandwidth for all of my links. Here I can say, I have, out of this site, 4 paths. I can use each of these paths to 75% traffic utilization. Because if any one link fails, I take the traffic that was on that and move it onto the remaining 3 links. So I get much better utilization of my network over time as well. And I can do that in a global scope. If I do this with classical tools today, a router here would only do that traffic reengineering based on the data it knows. Here the controller has a global view, and the controller can say, well, this link failed, so the best path to get here would be to go here. But this link is already hot, so I'm actually going to send traffic that was going here, originally this way. Best path might say go this way, but for the global health of the network, it makes sense to put this flow that way, because I get better utilization of the overall traffic graph, remaining traffic graph. Go ahead.
Do you propose to,
And your name?
Mike from Mixia. With this proposal, would you say you pre-provision with primary path, and then upon a change or when you're tuning your network for traffic, then you're proactively re-provisioning it? But I guess the question is, outages happen and you need to recover in, let's say, sub 50 milliseconds. So would you already have a primary, secondary kind of thing already defined and then do tuning? Let's say when management, when the ops center deems it necessary?
So different operators have different views on this. I'll give you what I've done before doing this with custom software and earlier generation technology, not Ethernet. I did a primary path and a backup path, pre-provisioned into the network. And then I had the behavior for when it's all gone to worms. And I've had massive, basically I built primary and backup paths that would solve for any single outage in the network. If I had multiple outages in the network that were in pathological locations, you then let the network, what you're doing here is allowing this core router to see this core router, for example, over what looks to the core routers as direct point-to-point links. However, this core router will still see this core router, and this core router will still possibly see this core router. So in a worst case scenario, if let's say this core router has lost its primary and secondary link and can no longer see these two together, it possibly can still see that one through this one. So you'll let IP routing solve the catastrophic problem. And then your ops guys go, oh, there's a problem, and you potentially regraph the network at that point. Or you could do it dynamically. Different people have different views about how much dynamicism they want in their core.
Okay, so the concern would be if you're relying on a communication of the controller and the controller push down a change, that time would be unacceptable to probably most operators.
So again, it depends. It depends on the product, and it depends. There's a little white lie about 50-second, millisecond restoration time across the country. If you think about it, it takes longer than 50 milliseconds for a photon to get from one end of the country to the other. So signaling an outage in 50 milliseconds sort of depends on your definition of 50 milliseconds. But there are things you could do. You could have switches so I could pre-provision primary and backup paths, let the switches detect if I'm going to use the primary backup using something like BFD, and once I've taken a backup path, go tell the controller that I'm on backup and I probably need a tertiary path calculated. So there's a number of different, again, this is a toolkit. How the operator, for example, would decide to use the toolkit is sort of dependent on the operator. Did that answer the question?
Yes. I think some of this is still to be defined with OpenFlow, and I think OpenFlow is going to need to leverage existing protocols like a BFT or something else anyway. So
sure. I mean, I think again, this is just at this point you just look at it as a toolkit to lay the paths in. There's probably the question is, do you extend to OpenFlow or do you wire OpenFlow into other protocols? It's I think that's yet to be decided. This is just putting a tool in the toolbox. The other one, multi-tenancy. We always talk about multi-tenancy in OpenFlow in the form of IaaS and multiple customers in the cloud. You'll notice I drew red and blue networks up here. Most service providers will run more than one IP network. And the reason being, most large corporates don't like the concept of their private IP VPNs running in the same infrastructure as the unwashed internet. The fact that all of their competitors are in the same piece of infrastructure doesn't seem to bother them. But the internet does, and this is a sociology question, but your product marketing group in your service provider will tell you that they can make a lot more money if they say that they have a private internet VPN infrastructure for their corporate customers. So we have a red network and a blue network up here. And one's the public internet, and one's the private infrastructure. Some service providers have more than that. Last one I was at, this was a double-digit count. It's an entirely different question that we can, in pathology, we can talk about that at some point in the future. But today, I have separate core routers, separate edge routers, and probably separate transmission to get them from one point to the other. So they're on different waves on the fiber. I'm not getting the ability to statistically gain. So I could have one wave that's 40% utilized for public internet and another wave next to it that's 20% utilized for private VPN. I'm still using two waves, even though it would quite comfortably fit on a single wave. And that's the way providers have built their networks. Wavelengths cost money because they cost router ports, they cost 3R ports in the fiber transmission system, and a whole bunch of things that, again, not topic for here. You can come up, we can talk about offline if you're interested. What if I use these Ethernet switches, these traffic engineering fabrics, to build separate disjunct meshes that tied the blue networks together and the red networks together? They shared the same fiber, they shared the same wavelengths across here, but they're kept disjunct at a logical layer by basically saying red routers can only talk to red routers and blue routers can only talk to blue routers. And the underlying fabric controls that. No control plane that's shared with the red routers or blue routers. So the concern is if the internet has a bad storm, the control plane on the internet side might upset the routing protocols on the private network and take the private networks down. So here you say there is no protocols at a routing layer between the blue and the orange or the red and the orange. Basically, you're saying there's an open flow controller that may be listening to these in some way, shape, or form for their utilization and putting paths in here. This looks like a single big Ethernet switch, these blue and red routers, and they can't see each other. So now I have the ability to build multi-tenancy and use most effectively my intercity bandwidth rather than using wavelengths to separate those traffic flows. Not saying you do it. Some people might. It's another tool in the toolkit. I'm using low-cost ports where forwarding decisions do not need to be global in scope. They're already made. Once I know the traffic in LA needs to go to New York, I really don't, in Omaha, need to know where New York is in the global internet routing table. I just need to know where New York is within the scope of my infrastructure, which is thousands or tens of thousands of devices, not hundreds of thousands of endpoints in the network. So I've constrained the amount of address space I have to look at. You constrain the amount of address space you have to look at in packet time, you massively reduce the cost of the platform. If that lookup table can be on chip in the TCAN without going off chip to high-speed memory next to the forwarding chip, the cost of the platform becomes cheaper. It frees ports on my high-value routers that today I'm using to do fairly non-value generating stuff to do interesting value generating stuff. High costs for customers who want to pay me to throw away someone else's traffic. I'm sorry, that's the impolite way of talking about costs. To value their traffic more. It allows me to do things with those ports where actually I'm extracting value out of those ports and I'm willing to pay more money for them versus doing something fairly mundane with them, which is just shipping bits. MPLS theoretically already does this.
Yes.
It does. What's the cost of an MPLS port today?
Very cheap.
Very cheap? At the bandwidths we're talking about on internet cores, I'm not willing to concede that MPLS ports are very cheap. They could be made cheap, but are they sold cheap today? Because frankly, those MPLS ports are on the same platforms that those core routers are at the bandwidths we're talking about. So the cost of those ports is approximately the same cost. Not saying they couldn't be built cheaper. I'm saying the industry has not delivered that in a long time of promising at those bandwidths. So you could do this with MPLS. To date, it's not deployed. What about those services? So that's one use case. And I guess I'm going to go into a second use case here, but that was a fairly big dump on service provider architectures and traffic engineering and economics. So is there any questions before I start? Hold on a second, we've got the mic coming to you.
Hi, Ewan Miller from Citrix.
Mm-hmm.
How much of that was fantasy and how much of that is in existence today?
So, frankly, you could do this today if you were willing to do the software yourself, the controller software yourself. So there's companies out there that make the traffic engineering software calculation software today. I did this exact network at Internet MCI 10 years ago, except these were ATM switches because that was the highest speed switch I could get my hands on at the time. And certain router vendors didn't have VLANs on their router ports. So even if I did have Ethernet, so we're talking 99-2000, even if I did have Ethernet, I had no way of building logical interfaces across that Ethernet fabric. So I did this 10 years ago with ATM. So did UUNet, so did a number of folks. This is not a new idea. What this is saying is take some new possibilities with OpenFlow to actually use even less expensive ports. I could build this, you could build a software yourself and use, say, port-specific VLANs to do this. And do VLAN switching all the way through, because 4096 VLANs isn't going to be enough across the whole fabric. What the controller allows me to do is solve a bunch of the problems with OpenFlow, solve a bunch of the problems, I see your question, solve a bunch of the problems that I'd have to solve on my own. Maintaining loop-free topologies, provisioning all the forwarding chips, etc. You could do it today. So,
it sounds like you just want to start it for you.
Actually, I'd say for the folks who need to do this, if you give them the tool set, they'll go off and they'll do this. I look at, static flow pusher concept in OpenFlow today. How much more do I need to do to make this work?
So, in fact, Matt Davey, Indiana University, we actually have a demo of doing exactly this on that network that you just showed, the Internet 2 network, using low-cost Ethernet switches, OpenFlow, provisioning primary paths, backup paths, and we actually have a web UI so our customers can go provision their own paths with bandwidth across our core as well, and it's actually going into production later this year.
Mm-hmm.
And it'll be at the demo session tomorrow.
So, pass the mic down to the front, please.
Manoj Patel, Google. I see that the controller's control path, one which is, pushing the flows and other thing, requires much higher availability of the links that it goes through than the traffic. So has there been some thought on the control plane of this whole OpenFlow?
So I'd argue that the individual paths may not need to be resilient, but I need to have a way for some controller. So if we think about a set of cooperating controllers, you can see where you might have multiple controllers bound to each switch. Building anything with the assumption that you can survive a single point of failure and will throw lots of money at it to make it really, really reliable is a really, really bad idea. And most service providers will tell you that the thing that you think absolutely positively cannot happen will happen. So plan for failure and design your control path such that it can survive multiple failures. An example I'll give real quick, I know there's another question over there. An example I'll give real quick is, what is the likelihood of having two fiber paths break within 1 hour of each other that stitch an entire state in a large OECD country to the rest of the world? Probably fairly limited, but it has happened. No matter what you do, there will always be, Murphy will find you and punish you. So assume that Murphy is out there and design appropriately. But that isn't an OpenFlow problem. That is a network architecture problem. That's why the carriers pay the architects the big bucks. Well, not anymore, but that's why they theoretically pay the architects the big bucks.
Yeah, coming back to the availability. So think about this network and this maybe 100 routers. So do you see a mind shift from the people side? Because in the past we had this 100 different routers to have 100 different control planes for fault isolation, for workaround of fingering of people. So now if I say I'm controlling this 100 routers by 4 controllers, and I'm doing something weird on one controller, I'm screwing up my whole network. So do you see some mind shift that people see, okay, we no longer want to have this independent control planes?
Actually, I would argue that fat fingering on a BGP route reflector can screw up much more than your 100 routers. So actually, I would say that the operational control on this is really no different. If I fat finger on a BGP speaker and my peers, for example, don't have the appropriate route filters in place. Of course, every service provider has completely accurate route filters, right? I can tank whole portions of the world. I'll point to the YouTube problem, right? So actually this, in global scope, is probably less of a threat than fat fingering a BGP policy. And actually from a scale size, when I did this previous technologies, this was a couple thousand routers. And folks that we have been talking to already have been talking in terms of tens of thousands of routers in a mesh like this. So it's not 100, it's much bigger. You could also use it for a smaller network. But yes, you want to, but again, it's a programmatic controller, it's a programmatic API. You put whatever code you want to write around that to make sure that somebody hasn't done something stupid. I would seriously recommend you do that if you decide to do this path.
So, Mike Howe from Michigan. Just to comment on a couple of those questions. The idea of separating control plane, data plane is not new. I mean, many of us know that. And there are technologies like MPLS-TP and PBB-TE that have been used and are being used today and being deployed. I think coming back from the Carrier Ethernet World Congress last week, the idea of this software-defined networking and having an API and having a common language for the programming and making it maybe one common feature set that can be supported across many different vendor equipment is really where the value is, especially that you can get beyond the network infrastructure and actually provision all the way into the VM and into the what is now called the cloud, not the WAN cloud, but the data center cloud. I think that what we're kind of seeing from the transport folks is first implementations are definitely in hybrid mode. It's just another method of, let's say, traffic engineering or another way to build forwarding entries. But I think future looking, you can get to a transport network that is simpler, cleaner, like is being proposed here. But I think certainly from the transport folks on the cutting edge, they're looking at just an additional protocol supported on the existing product line. In fact, one major NEM had it running, had a demo working at the Carrier Ethernet World Congress, showing software-defined networking working. So I think that's really interesting to the core providers.
So somebody, I'm surprised, hasn't raised the, well, what about optical bypass? We're down to 10 minutes. I've only done one of 3 use cases. So I'd like to go on to the next use case. If anyone was about to say, well, why haven't you done why not optical bypass? We can probably take that offline down here afterwards if people are interested in that conversation. There is a reason, and it's stat gain 20 years ago, guys. Get over it. Okay, what about those services? One of the things that's happening in a number of parts of the world, not so much in North America yet, is that either regulators or governments or communities are starting to sever the monopoly or duopoly of access into the residence or the business from the large RBOCs and PTTs and cable companies. So I look at the NBN project in Australia, where the government's spending a very large amount of money to drop fiber to most residences in Australia over the next 10 years. New Zealand's doing the same path. Singapore's done the same path. A lot of that's already happened in Sweden and some of the other Nordic countries. The UK keeps on playing around with the idea. So there are a lot of places where all of a sudden it might be that the service provider you know and love today, love in quotes, may not have a monopoly on connectivity to your house. Now what do we do? Because frankly, as a service provider, the services we offer is usually somewhat below the scale and below the capabilities you can get from the over-the-top guys. If I no longer have the nice ability to say, well, you're on my network already, use my service. It may not be as great, but it's pretty good, and you've got low network latency to get to me, and it'll give you a discount on the bandwidth, just buy my service. That linkage is being broken in some places. So now I have to actually compete on the services I offer. It's a scary thought. So, how I can compete is potentially still play on the concept of network geography. My internet-based backup service is going to be faster than Mosey or Backblaze because the server you're backing up to is in the exchange 50 miles down the road, not on another continent. So there's still things I can do to differentiate myself. I just need to make it easy for you to be on my network. So, problem is, once I've gotten that monopoly severed, I now have the same problem everyone else does in getting a customer connected to my network. And for the over-the-top guys, the cost of connecting to my network, i.e. making that customer available to your network, is asymptotically approaching zero, the previous graph a while ago. It's internet connectivity. So I want to, and I'm just going to play purely on internet connectivity, I don't have much of a dog in this fight. I have to now be as innovative as a Google, as a Facebook, as a whatever, and most service providers, frankly, aren't set up to do that at that scale. Some are putting in infrastructure to try, but they're not there yet. So I want to make it easy for customers to try and buy services on my network, hooking them up to my network, and then allowing them for basically very low cost to me to hook them up to my network, and then allow them to try services, buy services for an hour, a day, a week, come on and off my services list, which is what they can do with an over-the-top provider without me having to do a port move add change, which takes me 2 weeks, a union guy to go in a truck to an exchange in the middle of the desert and repunch some wires. That cost is a little bit high to do that. So what can I do? This is basically what I was saying. The serviceable ports, the way I deliver services today, I hook customers up to physical ports that provide those services, or to expensive ports that will route them to those services. And different services are on different physical ports. The number of customers, especially as an enterprise, who have multiple pipes to the same service provider to deliver different services. You got your VoIP network connection, you got your VPN network connection, you got your public internet network connection, all of these things going. You have separate pipes because guess what? It's separate equipment from the service provider. Different service providers solve that problem differently, but it's still a problem. How about on that same Ethernet switching fabric in the exchange, I hope customers, almost all the connection mechanisms at this point are Ethernet, are going to Ethernet. Stuff off the back end of the ATM, of the DSLAMs is no longer ATM, it's Ethernet. Off of the 3G, it's Ethernet. Off of the FiOS or whatever fiber mechanism, it's Ethernet. So how about you connect the customers to OpenFlow enabled switches? When the customer signs up for a service, I then install an OpenFlow flow in that Ethernet switch, in that OpenFlow enabled switch, for that customer and that service to direct them to the service port that I've already bought, but now I can use more efficiently by basically saying, here is a port that does VPN, here's a box that does VPN services. Instead of hooking customers directly up to that, and they may or may not be using VPN, and I'm going to have to charge them for the cost of that port. Now, when they want a VPN, they get routed to that box. I charge them for their use of a VPN service while they're doing VPN, and when they're not, the path gets torn down. So now I can charge customers the way they want. They can charge per drink, per use. I can make the most use of my resources. So now instead of buying a VPN port for every customer who may want a VPN service, I now buy the number of VPN ports I need to handle the VPN traffic at that site that I normally experience. Even if some customers are on Monday, Wednesdays, and Fridays, and some customers are on Tuesday, Thursday, and Saturday. So I get more optimal use of my infrastructure. So in this example, we have added green. Green is a customer aggregation element. A bunch of customers connected to it. Now we have two services, the red service and the blue service. So customers up here are connected to this element. It's a fairly inexpensive element, and basically make it almost zero cost for them to connect. And the customer goes to a website and says, you know what, I want to subscribe to HD movie streaming and HD streaming for this weekend because it's the Rugby World Cup. So they subscribe. For that period of time they're doing that, a flow is installed on the ag switch that's connected to the customer, and directs that customer to an HD transcoder, say service, the blue service over here, and connects them to that. And when they no longer want that, their Rugby World Cup's over, they sign off the service. The next week, it's the Super Bowl. Some other user up here is going to reuse the same port and be connected to the same port that the rugby guy was using the week before. I get better use of my resources. My resources are now being used for what customers are paying for, rather than the assumption a customer might eventually want to use it. Any questions on that one? It's sort of an extension of the previous one. Okay. Cloud Time VPNs. How many people in the room here have signed up for or managed VPN services from your service provider? How painful was it? Not too painful? Okay. One of the problems service providers have is there are multiple different VPN platforms. So you have the roaming user VPN, which is usually based on IPsec or PPTP or something like that. They've got site-to-site VPNs, which are usually built based on a set of MPLS standards called 2547. These are two totally separate platforms in the service provider. They have to be stitched together somewhere in the network to allow, or not stitched together, to allow roaming users access to the corporate VPN infrastructure. A lot of these require provisioning. The IPsec, I may actually have to roll someone out to install an IPsec gateway at your site, or provision an IPsec gateway somewhere in the network infrastructure for your roaming users. I have to provision 2547 AFI-SAFIs and BGP and all of that in my MPLS network to support MPLS VPNs. There are tools that will help you do this, but it's still a provisioning exercise. And provisioning exercise in service provider realm means human interaction and human time. Cloud IaaS, infrastructure as a service, also needs VPNs. You get a customer who wants 10 virtual machines and he wants them connected on a private network. That's a VPN. Cloud services are not going to tolerate provisioning time VPNs in the cloud. Somebody's going to want that network and they're going to want it up in 5 minutes. I can tell you there's very few service providers where manual service provisioning ticket can be serviced in 5 minutes. 5 days, doable. 5 hours, if you got a really good provider. 5 minutes, 30 seconds, not. So the service provider is going to, if they're doing IaaS, and any service provider who's not building Cloud Fabric, if not for their own, just for their own applications, but to sell to customers, is you can have a conversation about the longevity of that service provider. They're going to need to have a Cloud Time VPN infrastructure. Let's say that multi-tenancy VPN infrastructure is based on OpenFlow. What's to say you can't put OpenFlow enabled elements at the customer sites? You might want to do that anyway because the customer might want to do a public-private cloud migration. They've got a private cloud infrastructure in their enterprise, and now they want to do shock absorption into your public cloud. Having the ability to have the multi-tenancy, multi-tenant entity A in their service in their cloud tied to this set of servers over in this multi-tenant domain in your public cloud, having those tied together so you can talk to one another would probably be useful. Maybe that means running an OpenFlow element somewhere in the customer's premise to allow them to do shock absorption and stand up networks as they see fit, to be part of that multi-tenancy in your public cloud. Once that goes there, it looks an awful lot like a VPN, site-to-site VPN. Maybe you end up with virtual NICs or something like that on laptops that listen to OpenFlow to build forwarding tables or tunnels or whatever might be necessary. Maybe because this has got to come and will have to be done at scale to work right, can it start serving some of these roles as well and be totally programmatic, dynamic at time that the customers want to stand up VPNs and want to interact with you rather than the time you force them to. By the way, it costs an awful lot to have a person manually interact on a provisioning ticket. if I can actually have it done by an API, that saved me a lot of money as well. So those are just a couple of ideas of where service providers, not in the cloud space, might want to use something like OpenFlow. Service providers don't really do well when there are multiple options to do the same thing. So this is on the VPN case. Classical circuit monitors, this is all in the VPN case. We've talked about it. The other thing I did mention is if I've got a service provider, Salesforce, and I've got 3 different ways of doing a VPN, they will be confused as to how to sell it, where, and when. Might even be different product groups. They might compete against one another. That happens. So, is it maybe time to revisit the way service providers think about VPNs in the advent of cloud? Well, the cloud demands the rest of the VPN world wants. Rapid provisioning, rapid spin up, rapid teardown, rapid modification. That's what we just talked about. Okay, I'm 2 minutes over, which means I'm 2 minutes into your lunch, but I'll stay here as long as people have questions, or I'll be here after for people to come down and visit. Please just leave your rotten fruit up there. Don't throw it at me. It hurts when you throw it from that far away. Any questions? Thank you very much.